Astronomers just published a catalog that changes everything we thought we knew about what belongs in our solar system. The document, released in December 2024 by a consortium of observatories coordinated through the International Astronomical Union's Minor Planet Center, lists 47 objects currently moving through the inner solar system that show properties inconsistent with native formation. They're not all interstellar. That would be extraordinary enough. But what makes this discovery genuinely unsettling is that they appear to represent at least 4 completely different categories of anomalous objects, each with properties that challenge specific aspects of planetary formation theory. Some show chemical compositions impossible for bodies that formed in our stellar neighborhood. Others have orbits that violate dynamical constraints. A few display both anomalies simultaneously, and 3 objects remain completely unexplained by any current model. Light takes time to travel. When you look at the moon, you see it as it was 1.3 seconds ago. Look at our sun, and you witness light that left 8 minutes before. Gaze at the nearest star beyond our sun, Alpha Centauri, and you see light that began its journey over 4 years ago. This is confirmed science. Every photon crossing space carries information about its source. And the photons reflecting off these 47 objects tell us something is fundamentally wrong with our understanding of solar system architecture. Before we examine each category and what makes them impossible, hit that subscribe button and turn on notifications. This is Cosmic Outliers, where we catalog the objects that break the rules. Drop a comment with which category you think is most significant, because what we're looking at suggests our solar system isn't as isolated or stable as we believed. The catalog emerged from a systematic review of objects detected over the past 7 years. With improving telescope sensitivity and automated survey programs like Pan-STARRS, the Catalina Sky Survey, and now the Vera Rubin Observatory beginning operations, astronomers are detecting thousands of small bodies annually. Most are unremarkable asteroids or comets in typical solar system orbits. But a subset shows properties that don't fit. For years, these anomalies were treated as individual curiosities, interesting outliers that might be explained by unusual but natural processes. When researchers compiled them into a single database and analyzed patterns, they realized these weren't random oddities. They represented distinct populations with systematic differences from normal solar system bodies. Category 1 contains 19 objects with confirmed interstellar trajectories. These are bodies like Oumuamua and 3I Atlas, objects with hyperbolic orbits proving they originated beyond the sun's gravitational influence. What makes this category significant isn't just that interstellar objects exist, we knew that after Oumuamua. It's the diversity within this population. The 19 objects show a range of properties that suggest they come from multiple source systems with different formation environments. Some are icy and comet-like, others are rocky and inert. A few show intermediate properties. The compositional diversity is too great to be explained by a single mechanism or source region. This implies the local interstellar medium, the space within a few hundred light-years of the sun, contains debris from multiple stellar systems, each contributing a different type of object to the wandering population. Spectroscopic analysis of these 19 interstellar visitors reveals chemical fingerprints that don't match solar system abundances. Isotope ratios for carbon, oxygen, and nitrogen show variations exceeding what natural fractionation processes can produce within a single stellar nebula. This confirms they formed around different stars with different metallicities, the abundance of elements heavier than hydrogen and helium. Each parent star's composition reflects the mixture of gas from which it formed, and that mixture varies depending on the star's location in the galaxy and when it formed. By analyzing these isotopic signatures, researchers can estimate rough properties of the source stars, even though we can't identify specific sources. One object in this category, designated 2024 QX7, shows particularly unusual composition. Its spectrum contains strong absorption features from crystalline silicates, minerals that form at high temperatures in the inner regions of planetary systems. Most interstellar objects show amorphous silicates or organic-rich surfaces consistent with formation in cold outer regions. Finding crystalline material suggests QX7 originated from the inner zone of its parent system and was subsequently ejected, probably during planetary migration or a giant impact. This object carries high-temperature minerals on a journey through space that's lasted potentially millions of years. The preservation of these minerals tells us about conditions during its ejection and the interstellar environment it traversed. Category 2 contains 14 objects with solar system orbits but anomalous compositions. These bodies are gravitationally bound to the Sun, moving on elliptical paths that keep them within the solar system permanently, but their chemical makeup doesn't match anything that should form here. The most striking examples show isotope ratios for oxygen and nitrogen that differ significantly from the solar composition measured in the Sun's atmosphere and in primitive meteorites. In planetary science, isotope ratios serve as fingerprints. Objects that formed from the same protoplanetary disk should show similar ratios because they condensed from well-mixed gas. Variations exist due to temperature-dependent fractionation, but these variations follow predictable patterns. The 14 objects in Category 2 show ratios that fall outside these patterns. One explanation is that these objects formed in different parts of the protoplanetary disk, where conditions were more extreme than we've accounted for in models. Perhaps they condensed at the very outer edge of the disk where temperatures approached interstellar values and the chemical environment differed from inner regions. When the solar system was young, the outer disk extended possibly hundreds of astronomical units from the Sun. Material in these distant regions might have retained chemical signatures from the pre-solar molecular cloud, the interstellar gas cloud that collapsed to form our star. If so, these 14 objects are pristine samples of pre-solar material that never fully homogenized with the rest of the solar system. An alternative explanation is more exotic. Perhaps these objects didn't form in our solar system at all. Perhaps they were captured. Early in solar system history, the Sun might have passed through a dense region of the birth cluster, a group of stars that formed together from the same molecular cloud. During this passage, gravitational interactions could have transferred objects between stellar systems. An asteroid or comet orbiting a neighboring star could be perturbed into an orbit that brought it close to our Sun. If the encounter geometry was right, the object could be captured into a bound solar orbit. This process is called stellar capture, and it's theoretically possible but difficult to confirm without knowing the detailed dynamical history of the early solar system. Object 2023 HW12 in this category shows the most extreme isotopic anomaly. Its oxygen isotope ratio differs from solar by more than 5 sigma, a statistical measure indicating the probability of this occurring by chance is less than 1 in a million. The object's orbit is also unusual, highly inclined relative to the plane where most solar system objects orbit, and with high eccentricity taking it from the inner asteroid belt to beyond Neptune. This orbit could result from gravitational perturbations over billions of years, but the combination of extreme chemical anomaly and unusual orbit strengthens the capture hypothesis. HW12 might be a visitor from another stellar system that was captured 4.5 billion years ago and has been orbiting our Sun ever since. Category 3 contains 8 objects that show normal composition but impossible orbits. These bodies have chemical signatures consistent with solar system formation, but their trajectories violate dynamical constraints. The most problematic examples have orbits with inclinations exceeding 90 degrees, meaning they orbit the Sun backward relative to planetary rotation. Retrograde orbits like this are rare among large bodies because the protoplanetary disk, from which planets formed, rotated in one direction. Objects forming from this disk inherited that rotation, creating the orderly prograde motion we see in planetary orbits. Retrograde objects require a mechanism to flip their orbital direction. Small asteroids can achieve retrograde orbits through complex gravitational interactions with planets, a process called resonance hopping, where the object gets kicked repeatedly by planetary gravity until its orbit flips. But the 8 objects in Category 3 are too large for this mechanism to work efficiently. They range from 500 meters to 3 kilometers in diameter. At these sizes, changing orbital inclination requires enormous energy input. Calculations show that achieving retrograde orbits for bodies this large requires either an extremely close encounter with a planet, which should have destroyed the object, or external perturbation from a passing star, which is statistically unlikely. One object, designated 2022 VB3, has a retrograde orbit inclined 157 degrees to the ecliptic plane. It also has high eccentricity, meaning its orbit is very elongated. The combination produces a trajectory that takes it from the asteroid belt to beyond Saturn, moving backward relative to everything else. Dynamic simulations attempting to reproduce this orbit using known planetary perturbations fail. The orbit is stable. It doesn't cross planetary orbits in ways that would lead to ejection or collision. But how it got into this configuration remains unexplained. The leading hypothesis invokes the possibility of a close stellar encounter early in solar system history. If another star passed within a few hundred astronomical units of the Sun, its gravity could perturb distant objects into highly inclined retrograde orbits. Evidence for such an encounter is circumstantial, but these anomalous orbits might be the smoking gun. Category 4 is the most disturbing. It contains 6 objects that show both compositional and orbital anomalies. These bodies have chemistry inconsistent with solar system formation and orbits that shouldn't be achievable through known mechanisms. They represent compound impossibilities, objects that fail multiple independent tests of solar system origin. The probability of any single object showing both types of anomaly by chance is extremely low. Finding 6 suggests a systematic cause. Object 2024 DK19 exemplifies this category. Spectroscopic analysis shows isotope ratios for nitrogen and carbon that differ from solar values by multiple standard deviations. Its orbit has inclination of 134 degrees, with eccentricity, placing it on a path that crosses the orbits of Mars, Jupiter, and Saturn. This orbit is chaotic, meaning small perturbations produce large changes over time. Simulations integrating its orbit backwards show it couldn't have existed in its current path for more than a few hundred million years. Something placed it there relatively recently in geological terms. The combination of non-solar chemistry and recent orbital emplacement suggests external origin. This might be a captured interstellar object, but its current orbit is bound, not hyperbolic. Something captured it and circularized its orbit enough to trap it permanently. The mechanism for capture and orbital modification is unclear. Gravitational capture of interstellar objects is difficult because you need to remove energy from the incoming trajectory. In planetary systems with atmospheres, this happens through aerodynamic drag, but that only works for objects passing through gas giant atmospheres, and those encounters usually destroy the object. Gravitational assists from multiple planets can sometimes achieve capture through a process called three-body interaction, but the required orbital geometry is extremely specific. Finding 6 objects that apparently underwent this rare process suggests either we're missing something about capture efficiency, or these objects arrived through a different mechanism entirely. The remaining objects in the catalog fall into a 5th miscellaneous category. These show anomalies that don't fit the other 4 categories or combine unusual properties in unique ways. 3 objects in particular defy all current explanations. They show composition, orbits, and physical properties that don't match any formation or capture scenario we've modeled. These are the genuine outliers within a catalog of anomalies. Object 2023 QR44 is the most perplexing. Its spectrum shows absorption features that don't match any known mineral or organic compound. Laboratory spectroscopy has cataloged thousands of materials, and none produce the specific pattern QR44 displays. The features appear in both visible and infrared wavelengths, ruling out instrumental artifacts. Multiple telescopes have confirmed the observations. Either QR44's surface contains materials that don't exist anywhere else we've looked, or the spectral features arise from some physical process we don't understand. The object's orbit is unremarkable, a standard elliptical path in the outer asteroid belt, but whatever it's made of remains unidentified. Temperature measurements add to the mystery. Infrared observations measure thermal emission from solar-heated surfaces. For most asteroids, the relationship between solar distance, albedo, and surface temperature follows predictable physics. QR44 appears colder than it should be for its distance from the Sun and measured reflectivity. A colder surface implies either higher thermal inertia, meaning the material conducts heat unusually well, or active cooling through some process like sublimation of volatiles. But spectroscopy shows no evidence of outgassing, and the orbit's stability over millions of years makes ongoing volatile loss unlikely. Object 2024, FB8 shows different anomalies. Its composition appears normal, consistent with carbonaceous chondrite meteorites. Its orbit is typical for main belt asteroids, but its rotation is wrong. Photometric observations measure how brightness changes as the object rotates. Most asteroids show periodic variations corresponding to rotation periods between a few hours and a few days. FB8's brightness changes are quasi-periodic but chaotic, showing no stable rotation period. Over weeks of observation, the light curve shows complex variations that don't repeat. This suggests the object is tumbling in a non-principal axis rotation state, which can happen after collisions. But tumbling usually damps out over time due to internal friction. For FB8 to maintain chaotic tumbling, either it was recently impacted, which seems unlikely given its stable orbit, or its internal structure is unusual in ways that prevent damping. The third truly unexplained object is 2022 WX31. This body appears to be changing. Spectroscopic observations from 2022 show one set of features. Observations from 2024 show different features. The surface composition seems to have altered over 2 years. This is extremely unusual for asteroids, which typically have stable surfaces that change only over millions of years due to space weathering. Several hypotheses attempt to explain this. Perhaps impacts exposed fresh subsurface material with different composition. Perhaps thermal cycling as the object orbits the sun drives some chemical process that alters surface minerals. Or perhaps we're observing different regions of a heterogeneous surface as the object rotates, though this requires very specific viewing geometry at both observation epochs. The discovery of 47 anomalous objects forces a re-evaluation of solar system dynamics and formation. The standard model holds that our solar system formed from a rotating disk of gas and dust, approximately 4.6 billion years ago. The disk had a specific composition, the solar composition, reflecting the mixture of elements in the molecular cloud from which it condensed. Through gravitational collapse, turbulence, and chemical processes, this disk produced the sun, planets, asteroids, and comets we see today. The model predicts certain properties should be universal. Chemical homogeneity, with variations following temperature gradients. Orderly prograde orbits confined to a flattened disk. Predictable physical properties based on formation location. The 47 objects violate these predictions in systematic ways. The interstellar population proves our solar system is not isolated but continuously exchanging material with the galaxy. The compositionally anomalous objects suggest either capture from other systems or exotic formation environments we haven't modeled. The orbital anomalies indicate our understanding of long-term dynamical evolution is incomplete, and the unexplained cases remind us that we're still discovering new phenomena. The implications reach beyond simple census updates. If dozens of objects in our solar system originated elsewhere, it means material exchange between stellar systems is common. The galaxy might be more interconnected than we realized, with debris from planetary system formation and destruction constantly flowing between stars. This has profound implications for astrobiology. If rocks can travel between stellar systems, they can potentially transport microorganisms, a process called panspermia. Life might not need to originate independently in every system. It could spread, hitching rides on ejected debris that eventually gets captured elsewhere. The captured objects also provide a unique scientific opportunity. They're samples from other stellar systems that we can study in detail without traveling interstellar distances. Each captured asteroid or comet carries information about its birth environment encoded in composition, structure, and isotopic ratios. By analyzing these objects, we learn about planetary formation in systems we can't directly observe. It's reverse exploration, letting samples come to us rather than going to them. But there are concerning aspects. The orbital anomalies suggest our solar system experienced perturbations we haven't fully characterized. Close stellar encounters, planet migration, or undiscovered massive objects in the outer solar system could all produce the observed effects. Each possibility has implications for solar system stability and long-term evolution. If stellar encounters were common, they might have disrupted planet formation or altered the architecture of the outer solar system. If significant planet migration occurred, it could have scattered material throughout the system in ways we haven't modeled. And if massive undiscovered objects lurk in the distant reaches, they could pose future collision risks or cause periodic perturbations affecting inner system bodies. The unexplained objects are perhaps most troubling from a scientific perspective. Finding things we can't explain is exciting because it drives new discoveries, but it's also humbling. Despite centuries of planetary science, we're still encountering phenomena that don't fit our frameworks. This suggests gaps in our understanding that might be fundamental rather than minor. We might be missing entire categories of processes or materials that exist in nature, but haven't been incorporated into our models. Detection of these 47 objects was only possible because of recent improvements in observational capabilities. The Vera-Rubin Observatory, which began systematic operations in late 2024, can detect objects 100 times fainter than previous surveys. This increased sensitivity reveals populations that were invisible before. As Rubin continues its 10-year survey program, the number of detected anomalies will grow. Current projections suggest the catalog might expand to several hundred objects within 5 years. Each edition provides more data for statistical analysis and pattern recognition. International collaboration has been essential. The catalog combines observations from dozens of observatories across multiple continents and space-based platforms. Coordinating these efforts required establishing standardized observation protocols, data formats, and analysis pipelines. The Minor Planet Center served as the central repository, collecting observations, calculating orbits, and maintaining the master catalog. Without this infrastructure, individual detections would remain scattered across different databases, and the patterns wouldn't be apparent. Public data release policies have also been crucial. Most contributing observatories make their data publicly available after short proprietary periods. This allows independent researchers to verify findings and conduct their own analyses. Several objects in the catalog were initially detected by amateur astronomers using the publicly available data streams. The democratization of astronomical data has expanded the workforce analyzing these objects far beyond professional academics. What remains uncertain is the interpretation. We know these 47 objects exist. We've measured their orbits and characterized their properties. But definitive explanations for many of them remain elusive. The interstellar objects are clearly from other systems, but identifying specific sources is impossible with current data. The compositionally anomalous objects might be captured, or might represent extreme solar system formation environments. The orbital oddities could result from close encounters, planet migration, or undiscovered perturbers. And the truly unexplained cases offer no clear path forward without new observations or theoretical insights. Future observations will focus on several priorities: high-resolution spectroscopy to better characterize surface composition and search for additional absorption features, thermal measurements to constrain physical properties like density and thermal inertia, radar observations when objects pass near Earth to measure size, shape, and rotation precisely, and long-term photometric monitoring to track changes and look for activity. Each observation type provides complementary information that helps narrow the range of viable explanations. Laboratory analysis would provide the most definitive answers. Sample return missions to anomalous objects would allow detailed chemical analysis impossible with remote sensing. We could measure isotope ratios with precision exceeding spectroscopic methods. We could study minerals at microscopic scales. We could search for organic compounds and look for signs of space weathering. But sample return missions are expensive and time-consuming. Selecting targets requires careful consideration of which objects would provide the most valuable information. Theoretical work continues in parallel. Researchers are developing new models of solar system formation that incorporate processes we've neglected or underestimated. Close stellar encounters in the birth cluster, enhanced mixing in the protoplanetary disk, capture mechanisms we haven't considered. Each refinement brings models closer to explaining observations. When a model successfully predicts properties of anomalous objects, it gains credibility. When models fail, we know where gaps remain. The broader context matters too. Our solar system isn't unique. Thousands of exoplanetary systems have been discovered, and many show architectures very different from ours. Hot Jupiters orbiting close to their stars, super-Earths with no solar system analog, systems with multiple giant planets in resonant orbits. This diversity tells us planetary formation is flexible, producing many outcomes from similar starting conditions. Perhaps our solar system's architecture is less typical than we assumed. Perhaps the anomalous objects reflect that diversity. As we continue cataloging and characterizing these 47 objects and the additional anomalies we'll discover, we're building a more complete picture of what exists in our cosmic neighborhood and how it got there. The solar system is not a closed box containing only material that formed here. It's an open system exchanging matter with the galaxy. It's been shaped by events and processes we're still discovering, and it contains objects that challenge our understanding, forcing us to expand our models and question our assumptions. If this catalog of impossibilities expanded your view of what exists in our solar system and where it came from, hit that like button. Subscribe to Cosmic Outliers if you want to follow along as we track down each anomalous object and figure out what makes it impossible. And drop a comment with which category you think is most significant or which object you want us to investigate in detail next. This is Cosmic Outliers, where we're cataloging the solar system's outliers, one anomaly at a time.